concept.
I'm sorry, I just thought, does anybody object to me recording this? If you put it in the chat, okay, all right, fine.
Okay.
I do charge a fee for my image. I'm just letting you know.
Dave.
Okay, so what I'm presenting today is DIYnamics. It's an accessible, affordable, rotating fluid tank used to demonstrate ideas and concepts in geophysical fluid dynamics. So it's a model to explore the Earth's atmospheric, oceanic motions and some of the physics that is behind them. DIYnamics is a great community. It is a source for videos, teaching materials, different outreach activities, construction plans for 3 different types of tanks. And let's take a quick look at what one of the tanks looks like. So this tank here is a small acrylic vase, basically, on top of an OXO rotating turntable like you'd have in your kitchen. And so we have a Lego drive motor system set up, which turns the turntable at a constant angular velocity. And I have a Raspberry Pi with a camera so that the camera co-rotates with the system. Otherwise, you're watching the whole system turn, like watching the Earth from above, from a satellite, but you'd see the Earth turning. Here, you co-rotate with the system. The base cost for the vase, the turntable, the Lego parts is about $50 to $80, depending upon how complicated you want to get. So I have a remote which allows me to vary the speed of the motor. Otherwise, it'll just turn with a constant angular velocity. So what does this look like? So here I have a video, and let me speed it up if I can. Let's try that again. Okay, so what I have is I have a can of frozen water in the middle of the tank, which simulates cold Arctic air. We have a temperature gradient from the inside of the tank to the outside, and this leads to these eddies that form, which help transport heat from the equator, which would be the outside of the tank, towards the poles, which would be the inside of the tank, towards the frozen water. So I have food coloring added, which acts as a passive tracer. So this allows us to see the motions of these eddies, which are transporting heat. I'll let that play for a couple more seconds.
Real quick question. Where do you place your food coloring drops normally? Like towards center, towards the outside? Where do you?
So you can place them where you choose. So I tried to place the green more towards the cold air, and I tried to place the red more towards the outside, simulating the transport of cold air out and then warm air back in. But you know, you choose. It really a little bit of trial and error to find out where you get the best results. And so this was the first time I ran this experiment last night. It worked fairly well. And just to kind of show you what we're here looking at is this eddy transport in the atmosphere. And so we have red is this warm advection, this warm air being brought, or warm fluid being brought towards the pole, which is simulated by the ice water. And then the blue is the cold outflow. And we see these types of eddies in the atmosphere. And this is an image of water vapor from the pole. And so there is the North Pole. We have Alaska, North America, Greenland. Black is missing data, but you can see that the green areas are higher water vapor, and we have these types of eddies, which are being advected, which are being transported by these, with these eddies which transport moisture and cold air, etc. I'm sorry, green is drier. Green is drier, red is moisture. But yeah, water vapor acts as that tracer to a degree. So some resources, DIYnamics GitHub. Another great website is Weather in a Tank, which is by MIT. They have a series of experiments with quite a bit of resources, teacher materials, which describe the physics behind these geophysical flows. Are there any questions?
What age level or what group do you teach this to?
So if you're covering basic weather, you can have a basic demonstration to middle schoolers. I think it would be appropriate. You're not going to get the physics, obviously, but at least you can build the analogy that this is a model which kind of demonstrates what's happening with weather on the Earth in a rotating reference frame.
Thank you.
Sure. Other questions? All right. If there are no other questions.
Thank you, Mark.
Good
Good morning, all.
morning.
So, sitting around at home, and since I'm not teaching any classes per se, I thought, what can I do that would be useful if you were in the situation where you also were at home and all the kids were off, and looks like some schools are going to be moving more to that fully. So one of the things I picked up from my store of junk down in the basement is some filters, different things to put in front of the camera. One was a diffraction grating. This is a 500 lines per millimeter diffraction grating glasses. And let's see, now if as I do this, it might be a little bit easier to see if you're in the speaker view, so the speaker gets the main part of the screen, but you can choose anything you wish. Here I'm turning on the laser, and you should be able to see a few of the main dot, which you don't shine it directly into the camera, it just overwhelms it, but a little bit off angle. And you can see the individual dots. One thing about this, you could actually then use it to make measurements the way, if you ever looked at the gas discharge tubes and did that as an experiment with a diffraction grating in front of your eye, you can make the triangle, so you could, if you know the line spacing, you could find what the wavelength or frequency of the light is. And it's fairly easy to set up. And about the only thing you would have to do is make the distance measurements against some background that you see the dots projected against. Let's see this one. I'm not sure. My green laser has been a little. I don't know if you can see green dots. It's been going on and off. So I'll just give, the green dots are closer. And then of course there's back with this laser, and these are the $5 lasers. You can use the white light source, and then you can see the individual separation of the colors. And you could find wavelengths of individual colors, etc. So that's one type of filter that's been used. Another type, well, filter again, device that's used. Another is the simple red, blue. They often use them for 3D pictures, old 3D pictures. And so putting the filter over, and I'm going to drop this down here. And I have, where is it? There it is.
Hmm.
If you put the filter over, this is the red filter, and you see that the red one is pretty comparatively bright, whereas the blue one is dark. And if I switch it now to the blue folder, or blue filter,
Yeah.
the blue one should now seem to be pretty bright, and the red one is fairly dark. So if you end up getting to optics, and I realize that seems to be a topic that is not taught as much anymore. I know in formal curriculum, AP2, I think, has a section on optics, but the AP1, though it's got plenty of topics for kids to do, I did it last year, it doesn't include optics as one of them. So the old, if those who can remember, the old PSSC text and curriculum, which started with optics and became something that people made observations and then built models from. It was a really nice approach, and that just isn't the standard text approach anymore. So maybe someday again it'll return. And then one other thing, a couple things about and you may have known this before, but with the camera itself, I'm using a Mac Air Pro. No, not an Air Pro, just a Mac Air, sorry. And I'm shining a TV remote at it right now, and you should see the little light blinking. It so happens that some of apparently some have filters over the lens, so it doesn't pick up this, but this is sort of a near infrared that you can see the flashing occur. I've tried to use it with the diffraction grating to see if you can actually visually see a spread, but it's just too dim to notice the next, to notice the first maximum away from the central. But anyway, you can just use this to show that there is a light source that's coming, and we just don't happen to see it with our own eyes. So there's that. And then lastly, I think for this, I have just old pieces of Polaroid filters. And I found out something really strange, well, for me, strange, about the camera on this, and it's not the same on my other computer. If I put a filter right over the camera and then just rotate that single filter over the camera, it goes dark. And if I take another filter and sort of squeeze it in between, I know there's glare here, you might notice that sticking the other filter between the filter I'm holding and the camera, you can get some light to go through. And explanation is that there must be some filter on the camera itself such that the light that gets to it is in fact polarized. And again, I've tried this with my other computer here, and it does not have the same effect. And so you can do things with polarization, you can do things with two polarizers, but the main idea being that this is polarized here. And if you use the polarizers, you can use the cross polarizers and see, and in fact, then stick one in between. And the glare is pretty noticeable right now in here, but you can see it clear up a little where the one that I'm sliding in between is going. And there's one, that's it pretty much for demonstrations, although I was hearing.
Bob, we have a question for you.
Oh, yeah,
Mary?
looking at the, yeah,
Mary? Mary, turn on your mic.
So my question is just for kind of everybody, but with what is being done right now, how many people are using multiple camera setups? Like Ryan, Bill, and I in our summer program spent a lot of time kind of setting up multiple logins to Zoom, where I would use my phone and I would have two laptops set up so that students could have a look at my light board. I was using a light board. I was using a piece of glass in place of a whiteboard. And I was using my phone so that I could have kind of a close-up angle on experiments that we were doing in the classroom. And so I was just curious how many people have been playing with that kind of a setup, because I can see what Bob's doing right now as being something really spectacular to be able to have another angle on, so students can see your experimental setup, not just the cool optics.
Mhm.
So it's kind of a question for everybody.
Well, I know I don't have anything that's a sort of a second view. But I suppose that sounds interesting.
So you can probably see that I have a camera that's not my laptop camera showing my image. So I don't log in with two logins. I just use this camera. So that's on a thing that's hanging from the ceiling that's completely manipulatable, and I can just put it over my desk here, and so I just show without, they don't need to see me when I do the demonstration.
Dave
So
is
that's just an
chemistry.
old phone. What's that?
I said Dave is teaching chemistry, which why he is why he has the potions dungeon going on.
Yeah, I try anything to engage the students. I figure they're tired of looking at teachers' walls all day, so I
Where
had to
did you
do
get
something
that
in my basement
background?
anyway. So this is from Amazon. It's an actual tarp. Nothing's virtual here. This is from Spirit Halloween. This is actually one of my mother-in-law's candelabras with candles that bleed, and stuff I grabbed from the chemistry lab. And then this is also from Spirit Halloween that makes a little smoky, bubbly potion. So I got a lot of credit from the students for the effort. They kind of appreciated it. But anyway, the camera is just an old phone I had laying around the house. And I have a PC, but you can do it on Mac. It's just called, there's something called Droid Web or Droid Cam is the
There's
app.
a few apps for.
Yeah, there's a
flipping cameras.
zillion ways to do it, but it's basically just an old phone that was doing nothing. It doesn't have a phone number. It just works on Wi-Fi perfectly well. And so that's how I do like the demonstrations and stuff. And also, I just also want to mention for optics, I'm sure you guys do this. You guys know way more about physics than I do, but Pyrex and vegetable oil have the same refractive index. So you can actually make beakers disappear by putting them in vegetable oil, and the kids like go crazy that they can't see it anymore. Yes, BJ, that is exactly the reaction you usually get. So that's just another thing. It works much better in person, I think, than it would on the computer. They might think there's some special effects going on. But if you have a beaker without any lines on it or anything, it really totally disappears in vegetable oil. So just an idea.
All right, cool. So I also want to say before I go, I'm going to apologize that for a brief period of time, you'll see me muted because my daughter is applying to Downingtown STEM Academy right now, and I have to go pick her up from her essay. So in the world of Zoom, I'll be a picture for a little bit and then I'll come back. But I'll be listening.
So thank you, Bob. Were there any other questions for Bob? Okay, I think Art, you're next.
Oh, wait, can I say one thing?
Yeah.
What I wanted to share, maybe some of you have learned about this on your own, but I found it very useful as a modeler who likes to do whiteboarding. I was struggling with how do I get my kids engaged with presenting their responses to problems, and discovered a feature on Google Drive called Jamboard. If you've not seen it, if you open up a Google Drive, and go to all the various options, it is buried all the way down close to the end. But basically what Google Jamboard is just a white space where kids can write and do whatever they want. I forgot to bring my Wacom board here, but I've been gifted with the school districts a little device that allows you to write very neatly. I'll show you some of my examples, but it's called a Wacom board. There's probably other competing products out there. But what I've been using this is in my classes, not only for students to present, this is some of my students' work over here, but actually what I've been finding it very useful for is keeping track of my lecture notes. This is my honors physics class. We were doing position time graphs, velocity time graphs, motion maps. My lecture to them about the difference between what's a variable and what's a unit, which they don't seem to want to understand the difference between, and then some examples of graphing. So this is all one of my honors classes, and it's really helped me keep myself organized because it's, especially with hybrid teaching, hard to remember what did I do with the last class. It's also there for the kids to go back, and while I don't want to be taking notes for them, I'm just finding it kind of a useful way to help them stay focused and keep up with the class. One nice thing you can see here too is, I forgot to show this in the other one here, there's various backgrounds, and what I really like is you can import a graph paper background, which is very handy for this kind of applications. And then the other thing that I've been doing, this is some of my students' work over here. Students will be in their breakout rooms. We talked about that earlier, and I'm finding it a very wonderful way to keep kids engaged in small groups of 2 or 3 and that I can monitor. And then they will work out a problem on their own Jamboard in that breakout room, then save it and drop it into the class Jamboard. So you see here is one problem where I had 3 different groups offering solutions to, and it becomes a source of conversation then that we can talk about the different approaches to it, what one group did right, what one group did wrong, which those of you that are familiar with modeling, it's the same as a whiteboard session, as close as I was able to get to replicate it. So, and again, this is my handwriting with the Wacom board. You can see it's reasonably decent. And again, the development of the kinematic equation, some of the stuff I've done here with students.
These are all drawn with your mouse?
No, these are drawn with the Wacom board. All right, that was the, yeah, this is me with my mouse. Okay, I can't draw that neatly with my mouse, but the Wacom board allows you to have a stylus, and it's a little square. It's about 6 by 8 inches that mirrors your computer screen. And that's what you see here is the result. Even a little tree with an apple falling, for problems in free fall. Yeah.
Art, do you happen to know which Wacom board you have? Because they have a bunch of different products.
I don't know offhand. Again, I wish I would have remembered to bring it, brought it home with me, but I'll find out and I'll post it. Yeah.
This is the Wacom one. This was about $80 or so.
That looks like the same one I've got. Yep. Yeah. Okay.
And I've got the Wacom Intuos.
All right. That looks like the same one I've got too. So I don't know which one I've got then. They're all very similar. All right.
Can I interrupt? I just want to brag a little bit because in addition to Wacom,
ever shown. But I've got some slides I'm going to show quickly. And yeah, I hate the lag of like trying to find all your stuff on your computer at the same time. So this is my brief list of things that maybe worked. I've been trying a lot of stuff. I feel like the spring was really, really challenging. And one of the things that I felt in the spring was that I had like constant screen fatigue all the time because literally everything I was ever doing involved looking at a computer, whether it was teaching or going to meetings or grading things. Like I was on my phone, I was on the computer just like 24/7. So I've been trying to do more actual hands-on stuff with mixed results. Some of it has worked well and some of it hasn't. But I just wanted to share some of the really, really simple stuff that I've tried. I'm very, in our conversation, I've been very aware of like my privilege in being able to teach the way I've been teaching. So Friend Select has been doing either synchronous remote teaching or 50-50 hybrid where kids come in 2 days a week. And we just switched from hybrid back to remote because the test positivity rates in Philly are scary. And I mean, I'm at a school where I have an expectation that kids have their cameras on, and I'm not super comfortable with that expectation, but that's kind of my school culture. And I know that, you know, so maybe the things that are working for me may not work for other people, but this is what I've been trying. That has kind of worked. So the two things I want to talk about are hands-on individual activities for force and inertia, and just like really fast graphical lab results reporting. Hopefully it won't take too long because my toddler is mad at me. So these are just like straight up slides from my class slides. This one was with my 9th grade class. I gave everybody a care package with like a super ball in it, which I guess made them feel cared for, but they could obviously have a super ball without me sending them one. So clear a small flat area like a desk or chair. You're trying to push the ball in a circular path. And as you experiment, write down in your notes what you observe about the ball's motion after you push it and how you have to push. And I actually did this as a whole group activity, and I could see kids, you know, actually doing it on the screen, which was kind of cool. There's a way that having everybody's camera on them actually gives everyone, like, you can supervise everyone more closely in a sense than you could if they're in their actual classroom. So I had kids do this and then like private message me their answers, and, you know, chatted with the ones who were wildly wrong, and we had sort of a class discussion about it. And obviously the goal was like for them to see like, oh, the ball wants to go in a straight line. Oh, the ball has some inertia. And I know the sexy version of this, right, is to do like bowling balls and brooms or something in your classroom. And I've never bothered to get bowling balls, but this was something that everybody could sort of do at their house. And I think it worked reasonably well for kids to sort of discover the existence of inertia on their own. In the same category, we did this pencil and paper demo where you'd have a pencil that had to be round, unlike this one. And I gave kids these instructions. So, you know, rest your pencil on paper or a notebook and slide the paper out from under the pencil as fast as you can. What do you see happen? Which was pretty easy for kids to see happen. The object at rest part is pretty easy. And then the sequel was a lot harder, and I saw kids more like flying with things everywhere as they tried to implement it. So do the same thing, but this time I probably should be having you guys try them, but I know my toddler is like trying to get my attention. So rest them together, move them, and then stop suddenly, and what happens there. And my goal here is for kids to sort of see that it's the same thing both ways. I think they believed me better on the object at rest. They had more trouble like coordinating the object in motion one, but it brought physics into their classrooms or into their bedrooms, I guess. I have one more demo like this and then a screen share thing. So this third one was before we talked about adding forces with vectors. And most of my 9th graders are terrified of the Pythagorean theorem, which is a little bit awkward. But the general idea, I feel like, is something they can get. So they've got their ball, and they're supposed to sort of poke the ball in these different directions and look at what the ball does. And again, they were just sort of doing it in the whole class group. You probably could do it in breakout rooms, but you'd have to make sure each kid actually has the instructions in front of them when they're in the breakout room. So two forces in opposite directions of the same size, different sizes. I have not found a good way to say perpendicular in a way that every 9th grader actually understands. Drawing the picture is the best I could come up with. Perpendicular will fly past like half of them. But, you know, they tried this and they poked at the ball and they were able to see, you know, that it would go diagonal or it would go sideways or whatever, depending on which force was bigger. And that also seemed to sort of work pretty well for, oh, thanks, orthogonal. That seemed to work pretty well for getting kids to believe the idea, even if they really couldn't figure out the math. And when we've been doing the math for it, I've been trying to emphasize like draw things and measure them. And if you can't do the math part. Okay, so that was what I've done with my 9th grade class. And I think there's real power to this idea that, you know, the laws of physics are true everywhere. So I could have a kid, you know, who's in Vermont for the weekend or something, who can do the same experiment and see the same laws of physics. And in my advanced physics class, I can have kids like drop a ball and do video analysis on it. And, you know, the kid in China gets the same acceleration of gravity as the kids in Pennsylvania. Like, I find that really, really powerful. And that's not something we normally have access to. My second thing is super, super quick. This is just in advanced physics. We did some experiments and we collected some data on our own and we analyzed it. And I asked everybody to annotate. I got this idea from a friend who teaches college, to draw what their results were. Would you like to try? So I'd like you to try, I think I just enabled annotate, try drawing on this screen what your results were for your graph. There's probably on the thing that says share screen, there's like a little annotate button somewhere. And you should be able to draw lines on the graph to show what your data looked like. If anybody figures it out, just like guess, awesome, okay. I'm gonna wait for you to put your results in. These are some weird looking graphs. But as you can imagine, this is kind of a pretty powerful way of seeing what people's results were. And you can kind of see like, okay, so maybe it's supposed to be a parabola, but some people got a line and some people got something that like bent even more than a parabola. And it's pretty easy to kind of do your argument of like, oh, look, it is parabolic on average. Or, oh, look, okay, some of you got like velocity tilting up and some got velocity tilting down. But okay, it's basically linear. I also had them put their equations into a shared Google Doc, but being able to talk about the patterns with a picture and then referring much more briefly to the advanced physics lab results document, I think made it quicker and easier to understand. I also tried this for a 2-dimensional motion lab, which had more graphs, and I thought it basically worked. And it's just quick, right? And it takes less time than having kids draw on the physical whiteboard. So those were my things that I think worked. There were also a great number of things that didn't really work. And yeah.
Does anybody have any questions?
How long did it take to think like a 9th grader?
Someone sharing their screen by accident?
Yeah, I'm still working on learning to think like a 9th grader. It's very much like, oh, wait, this kid has this problem. And yeah, I don't know.
Is it harder teaching 9th grade physics than seniors?
They're just different challenges, right? Like 9th graders don't know stuff you expect them to know. And seniors refuse to ask questions for months. And then you find out they have a huge hole in their knowledge, but they were like too proud to let anyone know. But 9th graders are great at asking questions because they don't know anything. And you just have to figure out like, how much does that really mean?
I learned a lot by teaching 9th graders.
Did that popsicle realize that
whoever Pop Skull is, you're sharing your screen and everybody can see your photos. So
hello. Am I live?
Yes.
Okay.
You're a little faint though, so you may want to move a little closer to your microphone. Or do you have a headset that's plugged in still?
Yeah, I have a headset here. Is that better?
That's much better.
Yeah, I have you on speaker, but here's the mic. Okay, well, good morning all. This is fun. We're going to go from very high tech there to very low tech. This is about the time of year when often would make the transition from motion to dynamics or get into mechanics. So I'd like to show two demos. When I began learning physics, it was the beginning of the PSSC program back in the early 1960s. So I'm going to show you a little gadget that you can still get today that clearly shows the difference between inertia and weight. That's often a tough concept for any age. So let me undo the camera here and just hold it up. And can you guys see what I'm pointing at? Is that still large, Laura?
Yes, we were seeing a long.
Okay, yeah, it's kind of the reverse of where I'm pointing. Okay, so here's a device that you clamp onto a table or something, and it's made out of metal with blades here, like a hacksaw blade. I used to make them out of hacksaw blades. But anyway, you put some sort of standard masses here, and you can see it wobbles back and forth. Can you guys see that?
Yep.
So, you know, that's pretty fast. But with a stopwatch, you could time 10 of these oscillations. And if you put different amounts of mass here, the period will change. You know, no big deal. I think that's pretty obvious. But what was really cool is this particular object, the weight is right now hanging on here, but there's a string that's just attached. So if I lift the string, the tension is going to hold up the weight. Here we go. So I've eliminated the weight because it's on the string. So in a sense, now it's weightless, but it's not inertialess, and the period doesn't change. I thought that was really cool back when I was a teenager, and it's probably more cool now that I'm a retired physics teacher. Can everyone see that or see what I'm?
Yep, see it.
Okay. So you can buy these or make these cheaply. So one year when I was doing an experiment like this, and when I was especially teaching ninth graders, the ninth graders would take these meter sticks and, you know, play Star Wars with it. It's a great little sword. But as I watched the kids just horsing around in lab, I could see the way the meter stick was bending, that I could make something out of it that was an inertial balance, much cheaper to make than this one, but much slower period of oscillation, which is one of the difficulties. So here's a 1 meter long metal aluminum meter stick, clamped at one end by a 2x4. Can't see where I'm pointing here. So one end is fixed to the table. On the other end out here, I just put a little, you know, cup with a little holder here. So, you know, you can make this for a couple dollars. So right now there's nothing in the cup. Well, there's some clay there. So if I pull this back and let it bounce, you can see this is really slow. And even, all right, even a ninth grader could time that with a stopwatch, right? I don't want to belittle ninth graders. They're great. But there it is. It has a certain bounce with nothing in it other than, you know, the air and the clay. All right, so that's not showing you much, but what if we add a little bit of inertia? Here's 100 grams. So I put 100 grams in the cup. Now I pull it back and you can see, oh, that's bouncing a lot slower, right? Why? Why is it bouncing slower? Well, it's got more stuff, right? It's got more stuff to bounce back and forth. I'm trying to get the camera adjusted. So what you can do is put in standard masses like 50 grams, 100 grams, 200 grams, whatever. Here's a 200 gram standard. You have to watch, you can't put in a bowling ball, but you know. All right, well, that's pretty obvious. That's going much slower because it's got more mass, more inertia. Notice it's vibrating horizontally, so we're not fighting gravity. It's not like, you know, jumping on a diving board, bouncing up and down. So what we would do, what would have my students do is with standard masses, 50, 100, 152, 250, measure the period with a stopwatch. And instead of measuring one bounce, we'd measure, let's say, 10 bounces. A number didn't matter, except the error was a little less with 10 bounces. Then every table had an unknown. In my case, you're just a pool ball. By the way, the background is my ham Radio Shack. This is the man cave. So here we go with a pool ball. We don't know the mass. Oh, that's the idea. So you put the pool ball in here. The clay or putty or whatever you put in there just keeps it from bouncing around. Pull this back. So we don't know the mass, but we can figure out the time. That's pretty easy to do. So the goal was first to see that, oh, more mass, slower bounces. Let me put this back up here. All right, so more mass, slower to bounce. Okay. And now what I'd like to do is share the screen and I'll show you some sample data.
While you're screen sharing, Barry, I'm assuming you glued the cup to the wood?
Oh, no, I didn't. You could, but I just,
You just set it on top of the block of the wood?
I made a slit here. Oh, yes, this to here. Yeah, you could glue it. I put a little screw in or something. Yeah.
Okay.
So, I mean, this whole thing you can make, for nothing. Usually the cans or the tops had different designs or tuna fish cans. I just wanted something light. It also matters where you mount it, of course. The kids wouldn't know that, but you can change it by moving it closer or farther out. Anyway, these were all homemade, goofy, for a couple dollars. All right, let me see if I've got sharing. Is my share screen up?
Yes, we can see
All
your
right, I'm seeing something school district in Philadelphia. Let me close that. Okay. So I've got this. Is this live now? Inertial mass balance?
Mm-hmm.
Okay. So there's a picture. I can email you the instructions, but you'd probably come up with your own instructions. Couple pictures how to make these. You've got that. I showed you that live. Unknown mass. I used to do about a dozen labs with pool balls. It's amazing what you can do with collisions, with all kinds of things with, cheap Kmart pool balls. All right, so I don't need to show you any of this. We were talking about what is mass, and I said, well, here's a picture of the world's original kilogram. That was kind of fun. So this is, obviously in a vault in Paris. And here's the US kilogram, shiny piece of metal. That's in a lab in Gaithersburg, an IST. So here's what I would sort of give to them. So here's some standard masses, a 50, 100, 152, 250, unknown pool ball. Here's a summary of their data, the period, and what's their typical margin of error with the stopwatch. I'd have them time each object 5 times and get an average. So their data sheet would look like, let me just scroll down here. It would look like this. So 50 grams, time it 5 times, get an average, 100 grams, so forth. You can see. The unknown pool ball in my case, what was the average? 5 times. So that end up with a bunch of numbers, and I'd say, okay, so that was like the first day in lab. In fact, I sometimes would do this the first week of school because I thought it was a good teaching technique, as Bill Berner was mentioning. So here's some data that I got about a week ago when I played with this and set it up. So known mass, 50, about 11 seconds. This is time for 10 bounces. 100, 152, 250, unknown. So then, this was 9th graders mostly. They knew a little bit about graphing, so I had to go over with them, how you make an XY graph, what we're plotting. They had no experience yet, most of them, with fitting a function like a linear function, although some of them did because they had Algebra 1 in 8th grade. So this is a mix of 9th graders. So I taught them how to graph by hand. They would do that first. I said, well, just if the points look like they're lining up on a line, get a ruler and just draw a line through it. If they weren't lining up on a line, draw a smooth curve through it, So here was data. Then after they did it by hand, I showed them how to do Logger Pro or graphical analysis. They thought that was really cool. So at this point, they were learning about some math before they learned about it in algebra, which was fine. So here's the data I just plotted last week. Boom, 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 boom. Can you guys see that? That's pretty darn linear. All right. So we talked about what does it mean to be linear? You know, you double this, you double that, you double, you know. So they knew a little bit about relationships. Not everything in life was linear, but this was kind of nice because it was simple, and that's why I used it as a first lab. So in the case of the pool ball, they knew the time for 10 bounces. So I'd say, well, just on the x-axis here, find the time for the pool ball's 10 bounces, mark it. With a ruler, come up, see where it intersects the line you drew by hand or the computer line, and then come over here and read out the mass of the pool ball and try to get it to the nearest whole gram. Good enough. So they did it all by hand first, then they did it this way. And with an equation, of course, you can be a little more precise. We don't know it's necessarily more accurate. So all that took maybe 2 or 3 lab days, you know, a couple of 45-minute classes. They learned a little bit about inertia. They learned about how they might graph their data, how they could figure out what the mass of an unknown is. Of course, what they all wanted to know is, well, what's the real mass? I said, well, how are we ever going to know the real mass? You know, like, so we would have somewhere in the lab, you know, a balance that someone else made, you know, centigram or, you know, some balance manufacturer. I'd say, well, let's assume this thing's calibrated to the nearest 1/10 of a gram. They say it is. So we'll put it on there. So they get, you know, the true mass of the pool ball to the nearest 1/10 of a gram. And some of them were real excited because they got easily within 1 gram for a stupid meter stick bouncing back and forth. And they learned little about precision because I asked them, you know, what sort of uncertainty they have looking at their graph. What's the uncertainty and where they're going to plop their unknown timing. So there's a lot of things you could learn from doing this besides the concept of inertia. And then after that, I had a couple of questions that kind of stretched their imaginations, and I won't go into those in detail, but looking at this from the point of view of error, there's 2 big sources of error. You know, what you do with a stopwatch, or you could use a vernier photogate or something. So your timing error is obviously a source of error for both the knowns and the unknown. And the other is, how are you making a mathematical relationship, your curve? So I have a couple of questions here related to the fit, if we call it that, of their mathematics, or even their hand-drawn line to the known data. And then a couple of extra questions like, well, if you did it on the moon, would anything change? Well, we haven't even talked about gravity or anything. I just wanted them to start thinking about this. I think I can unshare the screen here and come back to live. Okay. Am I live again?
You are live.
Okay. So,
so
the whole idea was to sort of get them thinking about inertia, mass, weight, graphs, how you think in science. It has everything to do with what Bill was talking about. Why do you believe something? Well, here they saw the thing bounce. They timed it with a stopwatch. They tried to understand how they'd figure out, you know, a couple of them tried, you know, proportions or ratios, and sometimes that worked, sometimes they didn't. That led to a really good discussion about what's a proportion. You know, these are 9th graders. They're just learning about ratios and proportions. So throughout the whole year teaching 9th grade, I always had to teach them the mathematics they needed to do the physics at the time. So by the end of the year, it was amazing how much nice overlap there was between Algebra 1 or Algebra 2 or even geometry and what they were doing in physics. So I better stop. I'm over my time.
I was going to say, would you be able to either, I put the link in the chat, would you be able to add that handout into?
I've not used Zoom before, so I'm not familiar with what I have. You're all hearing me, right?
Yes, we can hear you.
Okay. Yeah, I'm not, we use Blackboard Collaborate at our college, which I'm very familiar with, but I'm not. So I want to share my screen to show the IOLab and some of the things that it can do, but I'm not exactly sure what I have to do here. I see your image.
At the bottom of your Zoom window, there should be a green button that says share screen.
Okay. Okay, so
you should be able to share. You should be able to choose what you're sharing.
All right. Let me see.
I can't see anything.
Okay. Are you seeing a screen that says IOLab datasets?
Yes, we are.
Okay. All right. The other thing I want to bring up. Let me go to the IOLab folder. And let me start, I guess, with this. I don't know how familiar any of you are with the IOLab, so I'll try to be brief, and then if you have questions, I also have one here currently, and to the extent that you want to hear about it, I can talk about it, but here's a brief overview. I teach physics of the geosciences at a small community college right across the... Sorry?
I can't see you.
I'm not showing myself. I'm showing the,
showing the data sets.
Yeah, I'm showing the screen that says, you should see something that says distance learning, real-time physics. Are you seeing that?
I have the IOLab data set, sensors.
Okay, why is it, so you're
This is
not seeing...
IOLab.
It will, if you selected to just show IOLab, it will only show that window, even if you have something on top of it. If you want to be able to switch between multiple windows on your screen, you're either going to have to switch sharing or you can share your whole desktop.
I want to share the whole desktop, so how do I do that?
So if you stop sharing what you're doing right now, stop what you're sharing right now.
Okay.
And then when you select share screen, the first option should be desktop.
Share screen, then look for where it says desktop.
Or
now you can put your camera on.
Share. Okay, are you now seeing my desktop?
Yes.
Yes.
Okay, so you see the picture of the IOLab then? Okay, so the IOLab came to my knowledge when the pandemic started in March and our college closed. We had to come up with ideas of how to do our courses. So I teach the 3 calculus course sequence for physics 1, 2, and 3. So that's mechanics, E&M, thermo, and then modern physics. I also teach algebra physics, a liberal arts physics. So I'm doing a lot of stuff across the physics spectrum. Our mainstay of teaching prior to the closing of the college was something called workshop physics, where we're very activity-based, very hands-on. We have the rigor of it being calculus-based all the way down to it being liberal arts-based. So I came across this device, and this device is nothing short of amazing. It's a little tiny box. It looks about the size of maybe a cigarette box on steroids. It's a little bigger than that, but it's got 13 sensors built in it. There are the people who were involved with workshop physics. One of them is named David Sokoloff. He got a grant from NSF to develop labs for this that he's offering free of charge. So you can get your hands on these labs to use with the box, provided you give them some feedback about what you're doing with their materials and how you're updating them. So this page here, I'd be glad to send this page to anybody who wants it. But this gives you a brief description of the IOLab itself. There are links on it. The software is free that works with it. There's software for the Mac. There's software for the PC. They give the directions for how to download it. And when you download the software, that's what I have behind here. This is what the software for it looks like. And it lists the 13 sensors here. So you have the ability to do standard mechanics experiments. There's something called the wheel. The little box has 3 wheels on it. Let me see if I can move that over a little bit so I can point to the box as I show you the sensors. So let me get my open here. And you're able to literally do, to be able to teach the 3 courses that I said, to give the students lab experiences at home, which has been incredible. So I'm bringing up this is what the little box actually looks like. Let me get autofocus on here. So I'm going to make this smaller and put this aside of the software. Let me see if I can do that easily. So it has 3 wheels, 1, 2, 3 here. When you flip it over, that acts as like it's detecting the motion. So the standard kinematics experiments we do with position, velocity, acceleration, you can get those graphs with this little device. It has a force sensor on the end here, so you can weigh things with it. It has a tiny adapter that lets you look at impulse. This little kit comes with it here. This little kit. So it's got a spring inside it. And what's really so clever about how you can do the experiments with it is just amazing. You use this humble clamp here. You put the clamp on the side of like a, well, I'll use my eraser here. But if this were a bookshelf and I put this like this, and I put this so it's like that, I can attach the spring to my IOLab and have it attached to here. And I can get, as the wheels move up and down the vertical shelf that you have, you're measuring the kinematic variables, and you can, it's got also an accelerometer built in it. So you can get some really nice, the lab I did with my class this week was just simple harmonic motion. We were able to generate some really nice graphs and data. And then, as I said, you can get simple kinematics data by just moving it back and forth. There's another adapter that you take this little hook out that measures forces. And when you put this other little adapter in, you've now got a platform for doing collisions. And you can do elastic collisions with it. You can get impulse. You also have another little collision device that lets you do inelastic collisions. It's got a little spring here. It's just absolutely amazing, all the things that you can do with it. And it's just starting to have people coming out with you know, more and more applications and labs you can do with it. It has a little dongle here that gets put in the USB port of your computer. And then this is communicating with your computer by radio frequency signal. So you can take data remotely as long as you're, you know, within reasonable distance of your computer. So that's another thing that's wonderful with it. So getting back to what the sensors are on it. So you have an accelerometer. You have analog sensors here for doing electrical experiments. So for my physics class where we're doing electricity and magnetism, we were able to do the standards, Ohm's laws, Kirchhoff's laws, Faraday's induction, magnetism. We were able to measure the magnetic field of the Earth, which I thought was really crazy. You hang this from a spring and you let it rotate around, and you're able, by the rotational motion, you're able to get what the Earth's magnetic field is. It's just mind-boggling what this little tiny box can do. It also acts as a power supply. So you have, they have here battery because this acts as a 3-volt power supply. It's got a barometer. So in my liberal arts physics today class, I had them follow a storm by measuring the pressure over time. I had not figured out how to use the electrocardiogram. There's 2 electrocardiogram sensors on here. It's a gyroscope. The high gain is an amplifier, so you can conduct simple measuring voltages. And they have a clever way of measuring current by using a very high power low ohm resistor and then reading the voltage across it. So in a sense, you have like a little ammeter. The magnetometer is really wonderful. Like I said, we were able, the magnetometer is just built right here at the top. Next to that is a microphone. So a couple of weeks back with my liberal arts physics students, I let them measure, get an idea of the voice print. It does fast Fourier transforms. So you can, you know, you can go ooh, ee, and then you can see what the frequencies are in your tones. So we were comparing, you know, what our different voice prints had in it. It's got a light meter, which I haven't used yet, but I'm going to do the 1/r² fall off with light with that. Let's see, I measured the microphone thermometer. And with the pressure sensor, another thing you can do, I haven't done it, but I've seen others do it. You can put this thing inside a bag, and then you can put it in, you have like a column of water. You can lower the bag in, and this little thing will record the pressure changes. So it's, now I'm a college, so we're able to, I recognize that in public schools, it's always about money. These cost, when you buy them at discount, $135, but the amount of physics you got enrolled in the box is just incredible. The Macmillan Company lets students rent them for $50 a semester. At our college, we bought some of these and we put together a shoebox. We call it our physics kit. And we put other little hands-on items that go along with how I like to teach physics. I don't just lecture, I always have people doing and feeling and seeing, kind of in the way you were talking about the Brownian motion. And then this with it as well, with those other little kit things that I put together for the different classes. We charge the students $50 to rent the box for the semester. And then if we get the box back in one piece, they get their full $50 back. But I could see the possibility of, you know, somebody buying these and then charging a modest fee to rent the box. You could build back what you had to put out money-wise. So I wanted to show with the actual software now, what David Sokoloff has made available are labs. So when you, that HTML page that I had up that lets you link to get this free software and to download it, inside this folder here, there are, he has 10 labs that he's made available for the public. And a typical lab, let me see, I'll go pull up my harmonic motion one. So a typical lab, this is one written by David Sokoloff. It looks like this, gives the objective overview. Now, as the students read these pages, it says save and go next, and then you just navigate across the boxes here. So it's talking about the energy, getting the area of the curve. This is some data that I took. Now the software has built in some things that are nice. I'm very used to using Veneer's Logger Pro and Pasco's software for our labs. But this, I was impressed that at first I didn't like it because I was so used to the other ones, but there's a little magnify function up here. So when you click on magnify, you can come down here to the graph and you can go and just get the data that you want to look at and blow it up bigger. So I can do that for my force versus time, which I measured for the harmonic motion.
Gail, we're running a little short on time, so
okay,
if you could wrap it up.
All right, so there's lots available. It gives very detailed instructions to the students how to do everything. So it's been one terrific resource, and if anybody wants any further information about it, my email is gwyant@cfil.edu. Done.
Thank you.
Okay, everybody can see me?
Yep, we can see you.
Okay, IOLab. Thank you, Abigail. We're working together. And I put on the chat to send me that information. Dave's PTRA, the Physics Teachers Resource Agent, in the AAPT membership. So we're colleagues, but he snuck that one in. Today I'm doing quadcopters, and it goes back to ancient times when people, the Greeks was jumping off the mountains trying to fly. So bringing it up into modern times, what happened to me was in the second grade, teachers was teaching us how to print, but I was doing things like this with the papers. It got me put in the corner for moments because I already knew how to print and write cursive. So going back into the early 20th century, when quantum physics came about, the Wright brothers was in Alexander trying to learn how to fly. He wasn't the only, they weren't the only ones, but there were others, but he had the documentation. So we had objects that could fly. And as time grew, just lost my tail. And my wheels. My plane is falling apart in front of everybody, but can you see it?
Yeah.
Okay, so my point was for it not to fall apart like that, but it's fragile. So what I'm saying is with the quantum, we start flying objects. And at that time, in mind, everyone was supposed to have a airplane in front of their house, just like the Volkswagen. So that didn't work. So we got objects, instead of flying, going up with a lift, right here we had a thrust that was going that way, and we had a drag coming this way, and the way the plane would go that way, and the lift would come up. So in the equation, that was the power. We won't go there yet. So here we had this object here, which is just a part of a copter. See that?
Can't see it.
Okay, we do it one more time. This was a toy that we had in the early days that doesn't want to cooperate. So we'll leave that alone for now. But it's the same simulation. And only thing we had to do, I better get up. Can you see it? It does that all the time. So my point is that this part here gave us the lift. So instead of having one, which developed into a helicopter, and we used for the wars came during that time, we developed more with quantum. So the quantum part is where we got into the science fiction. And the people during that time thought about not only just flying, but putting people into space with rockets. So a guy named Flash Gordon was popular during that time. And they made stories about it, which bring us into today where we actually are flying throughout the universe. But on the planet here, we had the quads. Now, hold on. This quad is nano size. Okay, so we couldn't see it, so we put it down. It got something more macro. So how this works is that we discovered a lot of lithium in the Far East, and we're using them for batteries. So here, it's called a drone, but it's an unmanned aircraft. And with this, we can it's very sensitive, so I'm gonna land it. So the equation for that is the power is equal to the momentum times the area with the velocity cubed over 2. And that's how we use it in physics. So what happens is with the copter is that you have 4 propellers, and 1 and 2 are clockwise, and 3 and 4 goes counterclockwise, and it gives us the lift. And of course, the weight is still involved in the thrust. So This is the larger model of how it works, because now moderately we have a GPS and we still have the propellers for our lifts. But the larger it is, the more it costs, so that we start making them smaller, and they ran by a Wi-Fi or radio waves. So if you start becoming a pilot, you can't go close to the poles where they're sending out Wi-Fi for Comcast and things in that nature. So since we had that smaller one, we have something that's larger than the nano size, that is small. We have drones that they use in fusion, that is size of mosquitoes. And of course, when you saw me last, I just had basically, I was showing you this one. But since then I've grown, and we have the transformer drone. All right, this goes from flying into a machine. Okay, so it's a tanker series. This is the racer, and it's ran by GPS and has video. This is a quadcopter that also has a QCI, and it's a real timer, and it also has a video which you use with your phone. This one here is a navigator. So it also runs by Wi-Fi, has a phone, and it's a compact drone with an HD camera. And this one is a super image, but it's just basically wires. And you have the base, but it also has a camera on it. And it's a video drone as well. Now, because the larger ones were so expensive, they started making smaller ones that do the same jobs as the larger ones. But we found that all of them run off of lithium batteries. And you always get batteries like this, or the smaller ones like these.
Jay, we're running low on time, so can
Okay, and finally, this is the the NAVAC Mini, where it replaces all the large drones, and you go up to 495 meters up in the air. So we're bringing classes, and hopefully very soon you contact me that we can have classes for drones, and you have it after school for all the physics teachers in the area. So stay tuned, or contact me if you'd like to get involved. We're making out and finishing up the curriculum as soon as possible, hopefully before January. So thank you very much.
Thank you, Jay. Does anybody have any quick questions for Jay?
How many misses were there before you learned to fly it correctly?
Oh, they're like wild horses in the beginning. You got to tame them and get used to their personality, because they will take off and just, we call them runaways. And I've lost 2, and I lost them in the park.
Do I have control over the screen?
You should, Bill.
Okay.
The little green screen share icon at the bottom
Yeah,
of your toolbar.
got it.
Where'd you get that Demo Day t-shirt?
Ah, see, I'm glad somebody noticed. No problem at all. You drive to Waco, Texas, and you go to Chip and Joanna's whatever place.
I knew it. I knew it. It's
And they got all this, because it's demolition day when they redo a house. And I went crazy. They got hats and shirts. And I said, you know, you got another whole market here that you got no idea of.
You know, you don't also have to drive to Waco, Texas. They do have an online shop.
Now that's cheating. Come on. Come on.
Bill, are you going to wear that for our demo day shows this year?
Yeah, you bet. You bet.
Are you guys having virtual demo day shows?
So Bill, Pete, and I just met yesterday to start planning E&M. We want to write to teachers about it. I'll put in the chat right now. We have a site with our demos. We've been recording for the professors and whatnot. So if you go to the Penn demo site, you can get access to what we have on YouTube already. But we are planning on working out a virtual demo show. We're going to try to make it part middle, like some strictly middle school and some strictly high school, so that we can kind of differentiate the discussion a little bit. And we're going to do some things live. We're going to have some stuff pre-recorded. We're struggling right now with concepts like, how many people do we let into that Zoom room? You know, like is it, if we allow, I think you can have up to 400 people. If we allow all 400 people in there, then should we really just be recording the demo because there's not going to be any Q&A? Or do we still have that kind of, you know, where teachers can, at least teachers would be able to have a student that has a question or something. We don't know. We're still figuring that part out, but there will be demo shows. The topic this year is electricity and magnetism. If you go to the link I put in the chat, you can get the Penn's demo library. There's links on that homepage of demos that I've recorded and posted, and also archived demos, which are just spectacular from Bill. So yeah, and I apologize if I just cut out there for a second. My daughter is calling to let me know, where are you? Because she's apparently done writing her essay. So
You're fine. Bill, you were sharing your screen and then you stopped.
Yes. Okay.
Oh, I was, okay.
And what am I trying to do here? Well, what I want to do is get to my camera. Okay. Where?
You should be able to, next to the camera on your Zoom window, if you want to change which camera you're using, you should be able to, if you click on the little arrow next to the video.
What I'd like to do is have the view from my camera show right now.
All right, then, yeah, change the, you should have the choice in your camera icon on the Zoom toolbar at the bottom of your screen.
It should say stop video, and then there should be like a little carrot next to that.
Right. Yeah, I got it. I just don't know what you guys are seeing. Because on my screen share, I don't have the camera view, do I? I don't.
We're seeing you.
He's seeing you, Bill.
Okay.
There
That's what I want to know. Okay. So my, you know, being retired, I got no trees to look at, so I end up looking at forests. And so take that in context. You know, I envy you guys being able to talk about details. My father was an aeronautical engineer during World War II. And he told me that one of the great failures that he had and that his occupation had was that virtually no airplanes fell apart in the air during the war. And that sounded strange. It sounded like something an aeronautical engineer would brag about. And he said, no, the problem was most of the planes came down because the crews got shot in them. And that they had engineered the planes without understanding all of the priorities. And they put too much weight into the airframe and not enough into the armor. And when I look at the situation we've got in the United States today, we're producing a lot of scientists, but we got 50% of the country that doesn't appreciate what they do. And I think we're in the same place that those aeronautical engineers were. We're doing a hell of a good job, but not really solving the problem. And maybe, as the aeronautical engineers need to do, you know, we need a couple more planes to fall out of the air and a whole lot less planes to have killed crews in them. And so what's the issue? And I think the issue is that we're teaching physics like any other, or science like any other subject. It's a bunch of facts that you learn and then you use on tests. And I think we've got to shift some of our focus. What makes science different, what we wish to hell the country understood, is that science is about the best way we have to know things. And we should take some of the emphasis off content and shift it to process. And in other words, you know, and let's see, what do I want to do here? I want to get to this. So to me, one of the things that's crucial, one of the parts of the process that's crucial is how do we know these things? And, you know, we do it differently in science. We start with observations and then we throw them out to the rest of the folks who are in the game and have them evaluate what we have seen and how we have interpreted them. The problem is at the current level, the game is played, you know, you got to spend years to understand what was observed and why people accepted or rejected it. And so I think what we need to do is to get back and hear the sentence that really, you know, while I was writing this, I realized, aha, here's my nugget. There are gems that are simultaneously easy to understand and of great scientific consequence. And we need to take advantage of those things. Some cases of that, and you know, we did that. I mean, for me, I began to realize that when let's see, yeah, I want to go down here. I was at a wedding this summer, and the father of the bride or the groom walked up to me, and I figured, you know, he's just going to say thanks for coming. He said, "Mr. Berner, it's so great to see you. You taught me physics and astronomy in 1974. And he described to me a viewing session behind the school one night when we had a telescope out and looked at Saturn and Jupiter. And it's damn near 50 years later. And this, you know, like, wow. We ended up doing something similar to that for reasons, you know, I was lucky there, but I learned from it. We put in the measurement of the speed of light. Speed of light is absolutely central to physics. And with new technology, it's actually pretty doable and it's really understandable. It's distance divided by time. And the students come out of it really feeling like they did some important science, which is critical. And so among the things that you might be able to do is Brownian motion. You know, none other than my hero, Mr. Feierman, has said that, you know, the famous quote in the first Feierman book, right here, if in some cataclysm all of scientific knowledge will be destroyed, what should we try to save? And what we want to save is the atomic hypothesis. Because in that one sentence, there's an enormous amount of information about the world if just a little imagination and thinking are applied. So Brownian motion was the point, and it's really worth noting. It's a great story, and storylines are a great way to sell your content. At the beginning of the 20th century, none other than Ernst Mach, inspirer of Einstein to general relativity, had said, "I don't believe atoms exist." Because even at the beginning of the 20th century, there was no observational evidence. Okay, it was a nice way to explain other things, but we had never seen them. Brown had observed vibrating pollen particles in 1827, and it went unexplained until 1905, when our hero, Mr. Einstein, published it as one of his 5 big papers. And the critical issue here is, you know, you can talk about all that crap, but you can see it. And so I've got a little bit of it here. You were talking about cameras. So if I can get back to, where am I? I want to go to this. And how do I get to my picture?
Try stop sharing and then go back into the share mode.
Stop sharing.
And then
go back into
You're back on now.
Okay, and are you seeing my camera?
No,
No.
just you. Go to your video options.
That's what I want. Okay.
Oh, okay.
Because I'm not seeing what. Okay, got it. But I'm seeing art. I want to, but whatever. Okay. So we've got a microscope here. All right. You can see behind me. This is my home.
Your home office.
Yeah, we moved.
He lives in his lab.
We moved a year ago, and my wife said we got to downsize, and I said no, we don't. We had a 13-room, 4,500 square foot Victorian that I filled with crap, waiting to retire to play with. And so, now is the time. So it all got moved. So this is a discarded microscope that lost one axis of its stage. And what I needed to do, it was low power. Some condensed matter fools were playing with it. God knows what they do. And to do the best way to go with Brownian motion is 600 power. So you want a 60 power objective and the eyepiece, because that's about as big as you get without oil immersion. And oil immersion is messy and a pain in the neck. Okay, so this is a 600 power objective. And before I left Penn, I got these guys to give me some styrofoam microspheres. So these are 1 micrometer spheres in water on a well slide, easy to set up. Okay, the problem is maybe you can't get them, and we'll talk about that in just a minute. And if you do not have a camera that plugs into your microscope, these damn iPhones work, which is nuts. It's absolutely nuts. So what I've got here is in essence a tripod. You can go out and get one of these magnetic mount iPhone holders. You get a piece of angle iron, put the magnet on it. It mounts with a 1/4-20 to any tripod you got, which is where we're at right now. Okay. And let's see. I think we are. And so this guy comes in here. And what I need to do is tell it to switch. Now I'm using EPOCCAM, EPOCCAM, and that lets you turn.
Wow.
Do what David did and get any cell phone to be, and so let's see, is this? So there are some particles, and if you look closely, okay, they are a micrometer, but the neat thing about the phone camera is you can enlarge it. And you can see focus is important, but you can see these little critters bouncing all over the place. You just play with depth of field. The other neat thing you can do with this is you can record it and dump it into video analysis, with Berner or any of those other things. And you can actually, go as deep as you want to into the statistics. Okay, the drawback here is that if you take a look at this, this is one of the companies that sells these things, and 1 micrometer spheres, it's $140 for a couple of milliliters, which is a pain in the neck. Okay, so your other option is to get a little more local and go to, let's see. And am I back on? Here.
Stop sharing. There you go.
So go to Wawa and get some light cream. Okay. And so now, if you put 3 or 4 drops of light cream and 20 milliliters of water, okay, we can just swap out. And where am I? I want to switch back to my camera, and I've got now, are you seeing that?
Yeah.
Okay. And all right, so are you seeing my, yes, there we are. So this now is, and we got to get, okay, so
There
now
it is.
this is cream. So there's globules of fat and there's milk particles. It's not as well calibrated, but in some ways it's a little better because the smaller particles move more. Okay. And that's a well slide and a cover slip and a 600 power microscope. And so now, like Ernst Mach, okay, the students go from having a faith-based appreciation to now actually seeing probably the most direct evidence of the existence of atoms that we can get. And this, you know, there are many simulations that can show you this. And I've thought that probably what I want to do is get a balloon and throw ping pong balls at it. And say, all right, if you blur out your vision, maybe you don't see the ping pong ball, but now you can see the balloon bounce around, which would prove that there must be ping pong balls in the room. And so, you know, that's essentially what I'm driving at is that, and in the paper that I wrote, I said, you know, like in looking back, I mean, I'm one of the guys who taught all of these folks who don't believe that the virus or climate change or any of this other stuff is believable. So I failed, you know, I'm like my father, you know, I built a plane that, you know, hasn't focused on the priorities. And so if I had it to do over again, I would try to find something like this and about once a month jump into it and have a thing where we took a look at, like, why is physics different? How when a physicist says that atoms exist, why is that different than when an advertiser says this tastes good? And you know, how did that get to be true? And you know, I think that that's really something that we haven't done enough of. And I think I've got pretty good evidence to the effect that that statement should be corrected at some point. And that's about it.
Excellent.
Thank you, Bill. Does anybody have any questions for Bill? Who currently looks like a...
Look at that. I answered every question. No, or I put everybody to sleep.
I think we're all just like salivating over your microscope mount and dreaming of what that could look like in our own class. But you're muted.
Hi, there we go. Hi there, folks. So I'm copying into the chat a document that I'm going to be talking through a little bit here. So this document is a link to my project that I had for Q1. So my school is one where we do a quarterly project instead of a midterms or finals or things like that. Basically, I was struggling for quite a while to find a project I could do in any sort of virtual schooling. And eventually I came upon the idea that, well, all of our students have cameras. We're talking about motion. And there's a feature in YouTube that I'm pretty sure not most of us aren't familiar with. But you can look up the frame rate of a video on YouTube. If you do a right click on it and you get the stats for nerds, you can find the frame rate. And you can also move the video frame by frame. If you pause any YouTube video and you press the period button, you will be able to advance the video frame by frame. As such, I figured, okay, let's have the kids record videos of things moving and figure out the speed of them. That's the project. Figure out the speed of an object just from your video that you recorded. That's the gist. all I've sent in that document is how I structured it. So I did a first checkpoint, which is asking the students to figure out how fast I was moving in a video that I made as a sample for them to figure out how to do this thing. I made a helpful video in that document, in that first checkpoint, to kind of show them all the things they need to figure out so that they could get that on YouTube, so they could do that analysis. And then the next checkpoint is for them to record their video and send that to me. And so I'm able to see if their video is something they can even get good data off of. And it's real quick, especially since the videos I'm asking for, I'm requiring that they are under 30 seconds long. Literally, they state their name, how wide their little, you know, those alternating colored bars, like the black and white bars you run past or whatever you might have seen in like when you're doing video analysis, how wide those bars are, and then what's moving across it. I got a lot of pets, which is really great. So I saw how many, saw lots of cats and dogs moving across the screen, as well as one lizard, which was super fun. Lizard was named Kevin. And then, yeah, they do their own after it's basically been approved in checkpoint 2, they do their own calculations on the video itself and write a quick report. This is a project in the form that I'm sending it to you. This is the COVID version. This is not highly rigorous, and I would probably do modifications on this to make it more rigorous for an in-person version of things. But it's a very simple and easy project to give students, and something they can do early on in the early on in the physics school year, in that, yeah, you've got all the tools. If you've got a phone camera, or if your district provided a laptop where they've got a video camera on it, which most of us have at this point, they should be able to do the project. And even in the school district of Philadelphia where I'm working, I have not had students that haven't had access to at least some camera where they could make a recording. And so, like, use the tools that are available and make a project off of it. And so that's all I'm gonna say. I've got a quick short presentation. I think I stuck to under 5 minutes, so we'll be able to move on to the next person. And that's all I got for that. So, and I have to run off after this. I actually have another appointment. So thank you guys for showing off all those wonderful things. And someday I'll see y'all in person again.
Yeah, amen.
Thank you, BJ. Mark?
Thank you. Right, so in the spirit of what Bill was saying, for many, many years now, I've been doing momentum conservation by setting up a Pasco dynamics track and crashing carts together in a carefully planned way so that the students can spot the pattern in what the final velocity is, depending on what the initial velocity of the incident cart was. And we just bring that around until I get them to formulate the result in the form of a conservation law. And so they have just figured out conservation of momentum. I talked about that a couple of years ago in a demo night, actually, and showed how it all works. And I now actually start the semester with that. It's the very first thing we do. Once you're done with momentum conservation, there is a very natural segue to figure out Newton's laws by thinking about when the blue cart hits the red cart, what it is the process by which the red cart's momentum changes. And we get to the idea of forces, and all of Newton's laws follow from that. But I had a really difficult time figuring out how to get to energy conservation the same way. And I finally figured it out. So let me just show you the first thing that I can, that's the segue, the thing that brings me into this. So when you do collisions which are magnets to magnet instead of Velcro to Velcro, so they're elastic collisions, I tell the students there is a second pattern which doesn't involve the masses. Look at the data, figure out what the pattern is. And everybody seems to get this, right? Which is that if you take the two blue velocities and you add them up, you get the red velocity. Or another way you could say it is the speed with which they're coming together before the collision is the same as the speed that they're moving apart after the collision. All right, so that and about 3 lines of algebra tells you that you can get that kinetic energy is the same after as before. So people would never have guessed that mv squared is a conserved quantity, but you can get to that just from 2 patterns that they have managed to spot. Okay, so having gotten that, the next question to look at is the question of, is it conserved all the way through the collision? Or is it just that you start with some value and then you come back to the same value? That's a crucial thing to know about when you're trying to get to Newton's laws. And it's absolutely crucial to do an experiment where you monitor the total momentum and show that it doesn't change at any time while the carts are colliding. If you do that with energy, you find there's a big dip. So kinetic energy goes away and then it comes back again. So this is a big mystery. How does nature know how much energy to bring back? And so I do an experiment to look at that. And the way to think about this now is, all right, so you can spend some time actually trying to suss out what could possibly be happening to make this work. And there's only one thing that I can figure out that could possibly be an explanation of this, and I'll try and show it to you now. So we have this result that when I do a magnet-to-magnet collision, this guy comes in with a certain amount of kinetic energy. Some of the kinetic energy goes away and then comes back again. And the only way that I can make sense of that is there must be something about the mechanics of this collision that takes some of that energy away and stores it somewhere and then brings it back. Right? It couldn't have just disappeared because then nature would forget how much has to come back. It must be stored up someplace. And the only way I can figure out that you can store up that energy would be in the separation of these parts. Right? That has something to do with the repulsion from the magnets, right? So if I put the carts this close together and I let go, that one gets some kinetic energy. If I put them closer together and let go, that gets more kinetic energy. So it must be somehow that by pressing these magnets together, I'm storing up some energy. All right, so if that's true, that means that as the carts come together, when they get, say, a centimeter apart, you've stored up a certain amount of energy. They get closer, and then as they push apart again, when they're again 1 centimeter apart, you must have the same amount of energy stored up that you had when they were a centimeter apart coming together. So that means the 2 times that they are 1 centimeter apart, the amount of kinetic energy that they have should be the same. All right, so I can now do that as part of the experiment once I've gotten somebody to actually raise that point. And in a moment, I will show you the crucial thing that you do on So here it comes.
I think what I need to do is to keep track, instead of keeping track of how much kinetic energy is in the system as time progresses, I need to keep track of how much kinetic energy is in the system and how it depends on how close the two carts are. Now, it so happens that in this very program, I have put together another calculated variable, which is something like the separation of the two carts. And I can make another graph of kinetic energy versus separation. And there it is. So this is a slightly funny looking graph. Here's what's going on. So we know that because of friction, we've been losing some of the kinetic energy in the system. So we started off with the carts pretty far apart. I gave the blue cart a push. It got closer and closer, so the separation got smaller and smaller. As that was happening, it was losing energy very gradually. And then all of a sudden they get very close together and the energy drops down. And then as they start to separate again, the energy pops up. Again, we've lost some of it, and now we continue to lose energy to friction. Now, the important thing is that when these guys get together, and I'm starting to store energy up in the separation between the magnets, if that's what's happening, I have the same amount of energy stored up when they're coming back apart as I was storing up when they were back together. So there was a time when the magnets were 1 centimeter apart. They got a little closer to that, and then as this guy sprang out, there was another time when they were 1 centimeter apart. And it looks like at those two times, I had the same amount of energy stored up in the separation, like the same amount of missing kinetic energy.
All right, so at this point, we've got the ideas of kinetic energy and potential energy that have both come out from doing this little experiment, just crashing some carts together. And so 3 of the most basic things from a mechanics course, momentum conservation, Newton's laws, and energy conservation, you can get at just by doing these collisions. So that's what I got.
Thank you very much. Does anybody have any questions for Doug?
Let me jump right in and say that I am an acolyte of Doug Kurtz's approach. I think he's absolutely spot on. One of the things that the next time we do one of these, the thing I'm going to talk about, like I say, I'm looking at forests now because I don't have any trees to work with. I have shelves of old physics textbooks. I am fascinated by old physics textbooks. And to me, the golden age was from about 1950 to about 1970 before it became big business. And textbooks were written by individuals. And boy, there are some jewels that didn't get wide circulation. And there is a book, Doug, I don't know whether you know of this book, Foundations of Physics by Michaels, Carell, and Patterson, 1968. And they do everything the way you do it. Newton's laws don't show up for chapters, and they start out with the interaction between objects and work backwards to momentum and then go from there to Newton's laws. And it's a jewel. And they open it up by saying, the starting philosophy is that a second order differential is not an explanation for anything. And, I found another copy of this, on Amazon. I mean, they're dirt cheap. Foundations of Physics, Michaels, Carell, and Patterson. Certainly you would be interested in it. And I think probably a bunch of other folks. It's one of those that really ought to be referenced to get away from the Resnick, Halliday, Sears, and Zemansky ossification of physics curricula. So that's
the
all.
Michaels. Is that the Michaels from Bryn Mawr College?
I don't know. Michaels, yes, it is Walter Michaels.
My wife was one of the graduate students there, and she can attest to that.
Yeah, it's a fascinating book. I really like it.
Yeah, I'm a definite advocate of the extreme position of making science students go through the scientific method.
Doug, I have a question for you in the sense that I know you teach at the college level at St. Joe. Does it make any difference from your experience? Does it make any difference what the students you're teaching had as high school students taking a physics course? Because everything you would have said must have reminded them of something they had learned or been exposed to anywhere from 9th to 12th grade, momentum, energy, velocities, all this stuff. You're not teaching the students for the first time. They've been exposed to, most of them have been exposed to these concepts in a high school physics class. Does that make any difference the way you're going to approach it?
I think not, because I don't think they make those connections immediately. So, if I crash two carts together and ask, how is the final velocity when they stick together related to the velocity that the first one had coming in? I don't think they connect that to something that they covered in a physics course in high school.
Oh, wow. That would surprise me.
I think part of that, the reason for that is I'm teaching bio majors who are juniors.
Oh, okay.
And so it's been a long time for them.
Yeah, they're not going to remember it.
Yeah.
I'm sorry. I'm teaching high school honors level juniors, and and they're not making the connection to order of operations when they're doing the kinematic equation. So the idea of applying what you learned in one class to another class is still sadly foreign. And that goes back to what Bill Berner said at the very beginning. We're teaching kids, to memorize stuff. We're not teaching kids to understand and apply.
Well, thank you to all of our presenters. We are definitely over time, so I don't want to keep you if you need to head out, but we